My name is Nicolai Josuttis, and I want and should talk about C++. And when Phil asked me about what I want to talk about, I decided maybe because we just have finished C++ 20, you can learn a little bit about it, but not only a little bit about C++, also about standardization and some flaws we had in the past. Standardization and concurrency again. So let's go. So let's start a thread. And how can we do that? We open a function foo and start it. However, as probably almost all of you know, there's a bug if you do it that way, because we have designed stdjthread in a way that before you destruct the thread object, you have to do one of two things. You either have to join it or you have to detach it. If you don't do that, the destructor will call terminate, which means you get a cordon, which in most cases, therefore probably is a problem. So you should join, for example, it, wait for this thread to finish before you leave the scope. Good, everything is fine so far? No, there's still a bug, probably. And the bug now is that it can happen that you don't get to the statement to join the thread, the started thread. And one example is you have an exception between starting the thread by declaring the thread object and calling join. So on an exception, in the meantime, you still have the problem you would like to avoid, and you might get a cordon. So what you really have to do then is you have to catch all exceptions that might occur and do something there so that you can finish this thread or call the destructor this thread without any problem. So for example, calling join there and then rethrow the exception or whatsoever. That's of course not nice. And there's something new. Something new available in C++ 20, which is jthread. It's just put a J in front of thread, and all you see here will be just done by calling a function, by initializing an object, and the destructor of the object will then, for you, join this thread. So we should have designed stdjthread from the beginning that way. I will talk about that a little bit later. But let me show you how difficult and tricky the problems with stdjthread are. It's almost impossible to use it easily and right, especially if you have more complicated patterns and more complicated code. For example, think about I want to create an object, and this object represents a couple of running tasks. These tasks run in different threads. So let's declare this tasks object and then start a couple of tasks. The arguments to start could be whatever you can call, so a function, lambda, or whatsoever. So how could I design it? How could I implement this class task? So I might come up with a pretty straightforward implementation, not using a standard container like vector allocating memory. To avoid allocating memory, I might use stdarray, so that I have a maximum but fixed size of threads I can start. You will see here an example. In my task, I have an array of 10 threads. And I initialize the initial number of threads by 0. So I have to count how many threads I have. OK, so we use the thread class as it was designed. Now, let's enable the API we want to have on the right here. So let's have a default constructor doing nothing. Everything is fine when we initialize the array and the number of threads. And then we implement start, and start will take any operation of type T, move this operation into a thread object, and increment the number of threads. So put it there. Of course, what is missing here is error handling if we have the maximum number of threads. So some assertions or some error handling is missing. But let's just concentrate on the key message of this talk. So now we have an object internally having a couple of threads, in this case 2. And when we call the destructor, of course, we can't just destroy the threads in the array. So we have to implement a destructor for that, and that's one problem with thread. So in the destructor of tasks, you run over all the existing threads and you call join. Good. It's a little bit a little bit bad that we have to implement a destructor here in this case, but it works. Okay. Now, can we copy a task, or can we move a task? Well, we can't, because we have a destructor implemented, so move semantic by default is disabled. And so only copy semantics would be enabled, but copying a task would require, or copying tasks would require copying a thread, which is not allowed. So we couldn't do something like this, what I want to do on the right. Let's initialize a couple of tasks and return them by value to somewhere and assign that somewhere later. So let's enable move semantic. That's easy. Let's declare that the move constructor and the move assignment operator is defaulted using the default implementation of move semantics. So now it gets interesting. Is everything fine with this code? Well, there's a bug. And this time, not probably, I think for sure. And this bug is a very serious bug, by the way, because if you now declare a new object task and assign it later, get tasks to it, you get a runtime error. What is the problem? Well, the problem is a combination of that the task is not an RAII type, and that we have move semantics support, and we have get now objects that go into a moved from state. And as you will find out and can see on the top, we get an invalid moved from state for the object. So think about the first part of this function, creating a task object. This task object has 2 entries, number of threads is 2, and 2 threads. The 2 threads are those I passed by as a parameter, so let's call them T1 and T2. So now what we have here is, unless things are completely optimized away, we have move semantic, which usually happens here when we assign to an existing task the return value of get tasks. And now we got a move assignment, and that means that we have here move the contents of this task object to T, to the new object T. The new object copies the number of threads and moves the thread objects. But with the default implementation of move semantic, the number of threads is only copied. So the object, the return value of get task, so the tasks object, which is returned here, is in an invalid state. And as you will see, this is an object where it says we have 2 threads, but the 2 threads were moved away. So we have a default constructed thread here, or a thread without an associated really running thread inside. And if we call join for them, which we will do now when we destruct the return value, we will get an error, well, an exception in this case. So we have created an object here, a moved from object, and we have created a state that is not valid. And we can't even call the destructor for this object. So of course you can argue, well, that's something we have to fix by better implementing the move constructor and move assignment operator. Yes, you can do that, but it could be easier. By the way, if you want to have some more details about problems like this with move semantics, you might be interested to watch on Monday my talk, my workshop about move semantics, 1 full day of move semantics, this and other problems. So again, we can fix that with a properly designed task thread class. So let's simply, since C++20 use jthread, jthread will for you automatically call join if we destroy a jthread object. And as and so we don't need the destructor anymore to do that. And that means that the jthread object that are here, the 2 jthread objects, which have no associated threads with them, will just do nothing, and everything works fine. We don't need the destructor, we don't need, and we don't get the problem that we have invalid behavior of this type if we implement the moving operations. Yeah, so why did we come to this problem and how did we deal with that? Well, it was obvious that class thread, stdjthread, is not the way we want it. So there's a long-going history about that we want to fix it. So right after we standardized it, in 2013, there was the first paper, and of course, that was a consequence of some discussion behind the scenes. So for example, Hapsada proposed 1 paper or 2 papers with roughly the same contents, which says the destructor of thread should join, so wait for the thread to end. And we discussed that and voted for it even, and there was we were strongly in the C++ standard committee in favor of this change. So we said 7 were strongly in favor, 7 just weakly in favor to make this fix, and 1 was weakly against, and 2 were strongly against this fix. But the fix was not done. It didn't get enough votes, enough support in the full plenary at the end of each meeting, where we finally decide about new features. So this vote you see here was just in an evening working group where we thought about this problem. In 2016, for example, Ville Voutilainen came up with another problem discussing the situation with thread and RAII. And again, we said we want to solve this problem, but too much time was gone. So the recommended path was to come up with a new auto-joining thread type with strong and weekly support about more than 20 people, and then only a few weekly against this. And then there was also the request, should we do that for C++17? C++16 was very close to feature freeze of C++17. Yes, there was support for that. But somebody has to do the work, and nobody did. So I started with this at C in 2017 and took the task to deal with it. And I proposed this new type called cooperatively interruptible joining thread. And it was discussed. And the interesting thing was, in that discussion, we had a lot of interesting discussion. One was, one opinion was even, well, explicit threading needs to die. I don't want to support anything at all anymore for thread support, supporting direct threading. It should be, should work with executors or coroutines or whatsoever. But in general, they said, yeah, go that path. But please include a solution for blocking functions. So if you have a condition variable on waiting and it waits for a thread, please think about how to stop it running when you want to end a thread. That was too much for me. I'm not a concurrency expert. So I said, okay, not my task. that's a problem of other people. Well, to implement that, it's my problem to use a thread class the way it was designed. So the consequence was that we got a re-request, I think it was raised by Herb Sutter in 2018, that we have now a couple of style guides recommend not to use stdjthreads. So they recommended to use something else. So for example, in one style guide, they had designed something like high integrity thread, or they said prefer the GSL joining thread over thread. And as he formulated, this was the community voting with their feet, almost to the point of rebellion, that we have to fix stdjthread. And because especially it turned out that all the replacements had bugs, significant bugs. And you will see later why when we talk about the design of the fix. So I come up with another proposal, and it took a lot of work in 2018 and 19 with significant simplifications, reference implementations, and especially merging this with a callback mechanism by Louis Baker. So that was the history. So let me talk about the design. It looks pretty easy how to implement the problem. What we need is a class, let's call it jthread, and where the destructor calls join if still joinable. So if join has been called, don't do that, otherwise do it. So how can we implement that? Well, it's easy. Create a wrapper around a thread, a jthread. And in this wrapper, we wrap the start of a thread, and we wrap, and in the destructor, we do something different. We join if we are no longer joinable. And of course, we have to think about a couple of other operations, but this is the main thing. So in the constructor, we get a callable, something to call with some arguments, both supporting move semantics, so we get them as universal references, or as some people say, forwarding references. And then let's initialize the thread object, which de facto means let's start the thread object, let's start the thread with the forwarded callback, so the object we want to call, and the, so it's a lambda or a function, and with the arguments we have. That's a variadic template here at the end, so we have a variadic number of arguments, which we pass through to start the thread. Because the interesting task and fix is a destructor. In the destructor, we simply implement if the thread is still joinable, join it. So that at the end, if we haven't called join before, we will join it. Okay. So that's it. That's roughly the design. This will join. However, it turned out that we wanted to have more, because we were now running into the problem that a destructor can now take forever, because the destructor of this object, and note that this might be called by an exception, might join, and joining the running thread, and the running thread might run forever. And the problem gets even worse, because threads might have started subthreads and they depend on, etc. So we raised, again, the idea that a destructor should stop the thread before it joins. It waits for its end. So a destructor should roughly kill the thread and not just wait for the end. Because obviously, we don't need it anymore. We discussed that. And we discussed a couple of design alternatives. There was a very helpful slide by Herb Sutter on that. And here you see the slide. This is a slide we have where we discussed which options do we have to deal with the request that we are able to cancel a thread. He distinguished between 4 different approaches. So the first approach is let's kill a thread. a couple of people think about the thread like a process. So you have a process scheduler, and you can just kill a process, even by kill -9 in Unix systems. And then everything is fine because the operating system will clean up. But that's a problem. That will not work that way. While some thread libraries have support to kill the thread, you can create corrupt transaction, some state that are not fine, corrupted memory. Read the POSIX book by Butenhoff, for example, for this, about this. So that is something you should avoid. Please don't never kill a thread. And by the way, that's the reason we don't have kill support for threads or for async in C++. So, but there are other options. So tell them, and tell them in a way that they have to cancel sooner or later. Herb said this is rude, and especially a design for languages where we don't have exceptions and unwinding, because that creates a lot of trouble in that. And or ask them politely, and we have that in Boost as thread, where we could call interrupt. And that, by the way, was one reason people were, even after years, still using Boost thread instead of stdthread, because they could do some, well, interrupt by tapping on the shoulder. It was designed by Jonathan Wakely, this class, or implemented. And it was a reaction, by the way, on the initial request that we should standardize stdthread this way. So stdthread initially in the first proposal had a way to interrupt threads, and that was implemented then in Boost, but not standardized. So we had it in Boost, but not here. So, and now send him a message. That was the other option, and that was do a cooperative cancellation. That means what I can request is, I can request to stop the running thread, but the thread should react on that, and manually, ideally, if it just sleeps, it should wake up and react on that. So, and that was a task we thought is the only acceptable way to implement it portably over all the platforms we have. Good. So the basic API from that was pretty simple. We have something to request to stop a thread. Let's call it jthread. I use a new terminology here, the final terminology. When we discussed that, we had very different other names. So, but just not to confuse you with all these different design alternatives, I use the wording when I can, which we finally standardize. So let's think we can start a thread, a new joining thread, and this has something to stop, to request a stop. And in the thread we start, we have something to check whether a stop is requested. For example, like here, while we are in a loop of doing something, we might here have a checkpoint saying, let's throw an exception if something is stopped. And the way we wanted to request a stop is something like here, that we, for example, request a stop here, or if we don't do that, just do it in the destructor. A couple of questions arise. Should we be able to signal stop from different places, so other places like here from the thread? What should, so the decision was yes, of course. So we introduced the concept of a stop token, so which was inside used in the thread, and we could use this token to request a stop. And but what happens if we copy and move this token? It was clearly, yes, we want to copy it to other places so that other places can signal stop. So it should be cheap to copy. But nevertheless, we need some lifetime. We have a communication between two asynchronous threads. So where do we store all the data, where they communicate about, and how do we deal with the lifetime so that it's automatically destroyed once nobody needs that anymore? Should we have the same type for requesting a stop and for dealing with a stop? Can we use a stop token twice? These are just a few of all the questions we had to decide upon. So let's implement and let's see the first way we implemented that, or I implemented that with the help of a couple of other people. So here's my starting thread. I start a jthread object, passing as usual the function I should call. And then this creates a stop token. So this is the token I can use to signal stop. And what we create here, a stop token, is essentially a shared pointer of an atomic bool. So because we have to share this information among different threads with different lifetimes, so a shared pointer seems to be fine, but we need to synchronize access to an information should the thread stop or not. And so inside the shared pointer, we have an atomic bool initialized with false. And then what the constructor of jthread does, it will pass this shared pointer to the thread local storage of the started thread. So we start another thread, and in that thread, we have some storage where you can find this token, the other side of this token, or another view to this token. So we can now use this token to find out whether stop is signal and to signal stop, and we can find out the information and even signal stop on the started thread. So now if we request stop here, which is, by the way, a shortcut to ask for the token and ask the token to stop, we will set this atomic object to true. And then here, because this is visible in the started thread, in this thread namespace, we can ask, was a stop requested? Or let's throw if a stop was requested. Here's a sketch how we implement that. It's pretty easy. jthread has two things inside now, a token and a thread. And we also introduced that each thread we start has a TLS token where the thread can check itself whether it should stop to run. So this is an inline static thread local object stop token. So that's a type. These are three qualifiers. So it's static in this class. So it's a static thread local object. So each thread has this information. It's a TLS object. And by using the new feature of C++17 called inline static objects, we could directly define it here in this header. We don't need a CPP file to define it. So before C++17, we could only declare it, but not initialize it. So, and now let's look how the constructor works. That's a constructor that starts a thread, so creates an object of this type. So let's first initialize the thread token by false. And then let's initialize the thread. And by initializing the thread, we start the thread, taking the arguments of the constructor as a parameter here inside a lambda. So we have to take the arguments, pass them as arguments to the lambda inside. This is what we call. We call this lambda with these arguments passed to this lambda. And then let's initialize the stop token of the started thread. So inside the started thread here, we initialize the stop token with the token from the thread we have. And then after we've done that, let's invoke the callback we passed. So instead of initializing the thread directly with the callback to call and its arguments, we first initialize its local thread local token by the thread token and invoke it. Okay. There's a bug. Who sees the bug? Well, I don't need an answer now. If I would now be in the room with you, there would be a lot of noise now. But think a bit. Think 10 seconds about a bug here. And this bug is typical for the problem we solve. Everything looks fine, maybe for most of us, other than you have seen the problem already. But here's a significant problem, which is a race, a data race. So let's look. If we create a thread object with some task to call, we call this constructor, and the constructor says, let's first initialize the thread token with false, so stop is not signaled. And then let's start the thread with the arguments I got. So we take a thread. There we have the lambda. The thread should start this in its own thread, taking the arguments. So far, so good. But you always have to think, if you have concurrent code, about that some things might happen earlier than others. And if code runs in parallel, you always have to make sure that any order is fine, and or in any order of execution. So what could happen here by the caller? The caller could immediately move away the thread to somewhere else. For example, move it in a collection of threads, like in the task object I had. So we call move for t, which moves away the thread token and the thread. This happens before we have initialized the thread object, but we have not started it yet. We start the thread, and now the thread is running. But in the meantime, we have moved away the thread, so the token is no longer there. This is broken. The thread token is no longer there, and so the initialization of the TLS token will not work. So that was the first time I realized that maybe there is something not that easy to implement. And it's a good example why we have, in general, the rule, every parameter we pass to a thread, we pass by value. But this way, we made a mistake. We captured our own member token by reference. Don't do that. So the fix is obvious. Introduce by value another token, and pass the token here. So once we have the thread token initialized and we start the thread, we pass our token. We already have created a copy here before we initialize, and that means before we start the thread. And now if the thread object, if data from the original thread were moved away, we still have our token and everything is fine. Yeah, thanks to Pablo Halpan. I think he was the first one who found this bug in my implementation. And I started to think, in concurrency, nothing is easy. So that means we have now a way to say, well, I should say, it turned out then that we didn't like the idea that we use thread local storage, because then whenever we start a new thread, the thread needs memory, at least for this token. It doesn't have to be initialized, but we need this in all threads. By the way, even in stdjthread then, and that price was too high. So we came up with a different approach, saying, well, instead of having thread local storage, let's pass the token by parameter to the started thread. So same design as before, but if I pass a function I should call to the thread, I add an additional parameter, which is a stop token, and which I can use to check for stops. It should work, though, that we can use a jthread like stdjthread. So we should be able that we can pass a function not taking a stop token. So the way we implemented that was the following. jthread had now a thread token and a thread. We were initializing the thread token and the thread. And now the thread taking the stop token by value, as just discussed. And now let's use a couple of new C++ 17 features, like if cons extra and is invocable v. So if we have a function that has a call able and then as a second argument a stop token. So if we have a function that takes a stop token as a first argument, let's pass it. Otherwise, we don't pass it. And that's a decision that's done at compile time. So that way, we could do both. Okay, that was the basic design. However, we wanted to have support for condition variables. And condition variables are a mechanism, for those who don't know, that we can let the platform have platform support to wake us up. So when we are in a thread and we wait for something to happen, we can just call wait on the condition variable, or wait for, so that which is a timed wait call. And then another thread can do something, and once it's ready, it can notify one or all of the other threads. There's one problem though, spurious wake-ups. It might happen that if you wait, you are waking up without a notification call. So for that reason, you always have to double check if you have woken up. It's like if your alarm clock rings, if you wake up in the middle of the night, it might be because your alarm clock did ring, or because you just woke up. So you double check the time, and if it's too early to wake up, you fall to sleep again. And that is implemented in our C++ API for condition variables. We have here an API you have to implement that is, if I have a wait function, I have to wait until I wake up. But if I wake up, internally, you have a condition that is checked. And if you just woke up as a spurious woke up, you double check, is the condition ready? And if not, you fall asleep again. So there's an internal loop here in the condition variable. And what we wanted was that we have here a stop token, the chance that I could also use a stop token here, and from another side, signaling stop and waking up this condition variable. So here's the way we designed it. So we said, okay, our stop token is extended now. It doesn't only have an atomic flag to signal stop. It also has a list of condition variables which are registered. And in the started thread, we get the stop token. And then if we have a wait call for the condition variable, so we want to wait, we want to fall asleep until we wake up, we pass an additional parameter, which is the stop token here. And that has the following effect. The wait call goes to the stop token and registers this condition variable. So in the stop token, we have all waiting condition variables. And now if we request stop, this is set to true, and we can go here in a linked list to all waiting condition variables and notify them, which means to wake them up. And that has the following effect. First of all, we have the end of the wait, so we remove the condition variable from the stop token, and then we can check, was a stop requested or was this a spurious wake up? So if a stop was requested, we can return. Okay, pretty tricky. Of course, it's not that easy. Here you have a linked list of waiting condition variables. So we have to extend that with a mutex because, of course, multiple waits might happen at the same time and they request to stop also. So we have to synchronize the access somehow to this condition variable. So in practice, we have, you can see here a little bit of the implementation, how this works. So this is a wait call. This is when we go to the condition variable and call wait. We have a new stop token parameter. So first of all, if stop was already requested, we don't do anything. By the way, it was an interesting question whether we should return whether the predicate is true or just return false to say, you can stop, nothing to do. And then we register this condition variable somewhere in the stop token. So there was implemented a register guard. This is not standardized. This would just be an implementation detail, a helper function doing the registration with the condition variable and its mutex, because for the access of the condition variable, we need a mutex. Otherwise, we have problems with synchronization. And then after this, we have a loop. The usual loop would be while we wake up and find out that the predicate is not true, so that the condition is not ready. Let's fall asleep and wait again. But now we have two things. We have this loop while we are not ready and no stop is requested. And inside the loop, and if we wake up, the internal loop will do the same and say, well, if we internally wake up and have this predicate of stop requested, and then everything is fine. But if one of these things happens, wait should fall asleep again and continue to work. Okay. So in real life, it looks like this. So let's do some real application of this scenario. Let's have a vector of values, a mutex, and a condition variable. So the mutex is to protect access to the values. The condition variable is to signal that there are new values in the vector. So in the reality, this condition variable should trigger threads that want to process some data from this vector. So let's create this thread, and it starts another thread getting the stop token. So they both have access here. So let's, in one thread, ask for some value and push back a value inside the vector. So we push a value, and then we notify all those who wait. This is, of course, protected by a guard, so that everything is locked here so far. And here we are running a loop where we wait, and our condition is that wait should end if the vector is not empty. So if it's not empty, we have some value to compute. We have here a lock. This lock will, for us, lock the values mutex. So if it's not empty and we wake up, we have some value and we can process this value. Of course, you have to be careful that the mutex does not block too long. But again, the wait will say, let's store this condition variable here. So when we stop, we wake this condition up. Well, reality is more complicated than this. So one interesting thing we came up with was this. Let's start a second thread, something like a watchdog process or so. And in this, we need some data of values. So we access a guard to these values we have. And if the value, the first value is less than 0, we request the stop. So the stop is not coming from here. It's coming from a third-party thread. And now things become very, very complicated because now everything has to work fine regarding races. So this could happen before this could happen before this could happen before this. So everything you had to double check that we don't run into deadlocks or race conditions or undefined behavior. And that turned out to be pretty complicated. I show you some examples here. We had a discussion by standardizing where we said we run into significant race conditions. Should we go back to polling, use a background thread to solve some problems, use recursive mutex, because recursive mutex would solve this issue, but condition variables don't usually support them. Should we switch to condition variable any, which would support any mutex? Should we restrict the specification of request stop? Or should we stop supporting waits? And this was all not good. Everything had significant drawbacks. So the only not drawback we saw is you should use condition variables, and then we can internally use different locks, and the user can call different locks. But we, with that, we have to internally introduce mutexes beside and in addition to the mutex of the condition variable we have. So that meant that the following happened. We took here a wait function, took a user log. That was a log the condition variable had. And then we would register this condition variable. And then we would have an inner log, which we internally use for the mutex, for the condition variable, request stop. And then we unlock the user log and called wait. So this was what we came up with. And you definitely don't have to understand why we came up with this. But again, we run into problems. And that's something I want to show you, because that's the things that can happen if we talk about concurrency. There's a significant bug in this code, and it's really hard to find. So the way this is used, look at this, is somebody calls wait. So it has the user, the programmer has a condition variable any, and it has and this wait needs a lock to protect the access for the ready, for something we check for being ready. So the requirement is that the user mutex behind this lock has to be locked by the programmer before they call wait. So then we enter this function, and in this function, well, we register our condition variable in the stop token, and then we have this inner lock. The inner lock, which we need now internally, one reason is because it has std mutex and not any mutex type we could support. So we lock an inner mutex, and then we have an unlocker because the user mutex has to be locked to do the actual waiting. This is the internal waiting, or you could also directly call here the operating system wait function. And which unlocks, this is an unlock guard, also an internal type. And at the end of this wait, we lock this inner lock again, and then we leave the function. And when we leave the function, we call the destructors of all these things, and the destructor will go backwards. So first call lock for the unlocker. So the user lock is the user mutex is locked again, and then the inner mutex is unlocked. And then the user gets a result and usually unlocks the user mutex. Did you get that? No, doesn't matter. So because usually you don't see problems like that, you just use a condition variable and pass a lock. However, here, this was very important because we found a bug here. Well, I didn't find it. I think one of the key guys in this group that helped me to implement it found it. And here it is. We have a user mutex lock, inner mutex lock, and here we have inner mutex lock, user mutex lock. So we lock the same mutexes, but with different order, and that's a recipe for a deadlock. So what did we have to do? We had to change the way we clean up things here. We first should unlock the inner mutex and then lock the user mutex. A way to do that, I didn't know this trick, is that we take the inner lock mutex, or take the inner lock and copy it to another object created later so that it first unlocks before we do the rest. Yeah, and this is just one example of all the problems we have. I just looked at my email, and here I saw some other problems we found when we had this implement the whole thing. So finally, the idea came up to generalize stop tokens. So if we implement that, let's implement a stop source and a stop token, but also let's introduce a stop callback. And instead of dealing with condition variables, let's deal with something we can call when we have a stop signal. And it turned out that we just took this to its own header file, to a stop token, because then we could use it in any other synchronous or asynchronous communication to signal stop from one place to the other. The plan is to use it in coroutines, executors, networking, I/O, etc. So the last change we had was when we waited, instead of registering a condition variable, we register a callback, and in the callback we call ourselves the notification for the condition variable. So that's the final design. The final design is, let's use condition variable. Let's start another thread. Excuse me, let's use here a stop token. Here on the left side, we have the stop source. That's the part to signal stop. And then the top stop token where we can check for it. And then call wait. Wait will then notify and register itself so that it gets notified. But we can also use our own callbacks to being notified when a stop is called. We can do that here in this thread, or here in this thread, or wherever. And once we request the stop, we will trigger all these callbacks, including waking up or notifying the wait, which means that it removes itself from this linked list, and that's it. And we can protest the value. And that's the basic design. So the cool news we have with the design you see here is, yes, we have now a class jthread. And if you learn just one thing from that, is wherever in your code you have stdjthread, replace it by stdjthread. And that was one reason for the J not having a very spoken name, is that your code should still look pretty similar. If there was some flaws in your code with this replacement, good code works as before. Everything works as before. Broken code get fixed unless in your code it was intentional that you get call-downs or exceptions when something goes wrong. Then please note that we have now in C++20 also not only jthread. Jthread are an application of a more fundamental feature that can help you a lot, stop tokens to signal cancellation. And in fact, all the problems I showed you about race problems, race conditions, are problems of synchronization for requesting stops. So we deal with a lot of scenarios where we can run into trouble. You can still create behavior that is that we are not able to solve, but in most cases, you will not get into racist, undefined behavior or whatsoever. This is trivially used in jthread, but you can easily use it in other threads. And of course, we have open issues. So we have only implemented interruptible waits in condition variables. So we can now support that and add that to other waiting functions, like for timers, mutexes, so timed mutexes, etc. And of course, in the next C++ standards, we will have support for stop tokens in other functions. The co-author of the implementation, Louis Baker, is, for example, coming from the implementation and standardization of coroutines, and will use stop tokens there to signal stops between coroutines. There's also a meta lesson learned from the experience I had. So what I learned from this, and that was 4 years, is yes, of course, concurrency is a nightmare. If you couldn't follow my slides on some tricky races, don't worry, I didn't either. So I thought about some of them, but the main work was not done by me, it was done by others. And so concurrency is a nightmare. And in addition, with C++ always being a little bit tricky because it's more flexible and more powerful than other programming languages, this is a big task. So you need test. In our standard implementation, in our example implementations, we have a lot of race scenarios to test. And this all would not have worked with just one implementer. So the resulting code is the result of a lot of really cool experts looking at the codes, etc. I just double-checked before I gave this talk, and I saw that I have about 1,000 emails about this whole thing in the last 4 years. And please never, never design a non-RAII type anymore. So where the destructor has to do something. But that was a very big design mistake in stdjthread. We knew them, but for some reasons I don't want to talk about, we didn't fix it early enough. But on the other hand, we now have a fixed RAII type with the ability to signal cancellation. And as you saw, we needed a couple of C++17 features like inline definitions and class template argument deduction and other things. So that helped us to implement the whole thing. Always being backward compatible is a goal. So we had to come up with a new type instead of the existing type. A few things that are not that self-explanatory. First of all, it turned out for me that configuration management for example implementations and even for providing papers to standardize the whole thing were helpful. So I had a Git repository, and it's publicly available under a Git, I think it's GitHub Josuttis jthread. You will find it in the internet. And you can see the story and the evolution of the implementations, and whenever we fixed some flaws or added a new test case and etc. Good naming is key. So you saw the final names. The final names is jthread. J stands for joining, not for Josuttis, but I can live with the other interpretation as well. So it's a joining thread, and by the way, it was not my proposed wording. But we had other names during these 4 years. So something like task or iThread for interruptible thread or whatsoever. And also stop token, the question, what is a good name for a stop token? Should it be interrupt token? Should it be cancellation token? Because that is used in other libraries. We finally decided to come up with a good name. We want to signal stop, whatever that means, not necessarily cancellation, so whatever we stop. And we wanted to introduce a new name because interrupt token and cancellation already has some meaning on some platforms where you could use similar mechanisms. It turned out finally that the task was far more complicated than I thought. And that means it turned out to be far more usable than I thought. So you definitely don't want to implement a class, a thread class, signaling cancellation or signaling stop yourself. You have only seen some of the problems. Look at the original source code, it's the example source code. Yeah, take your time to go through it. There are a lot of problems solved in this class. And the interesting other message is, it seems that non-experts can standardize. You might, I'm not an expert, I'm an expert, so you know my name, but I'm definitely not an expert in concurrency. A lot of the problems I showed you, I ran into them, I didn't see them, I even didn't understand some of the discussions we had about race conditions. But I was a driving force, so I was driving it through all the meetings, the discussions. I double-checked that I have experts to help me. And so yes, non-expert can standardize, can fix problems just by doing the hard work. And that's on you. If you want to have something, even if you're not an expert, there's a chance that you can have it and drive it and make it. So finally, I have to thank about a lot of other guys who helped me to bring this through and for C++20. So the main key contributors are for sure Howard Hinnert. I sometimes call him Mr. Modern C++ because he came up with all the crazy cool ideas of modern C++, like move semantics, concurrency, like here the thread implementation was his proposal, and chrono library, etc. And then we have Anthony Williams, of course, Mr. Concurrency, who has example implementations of everything, who has implemented Boost Thread and and gave me tremendous support in the implementation of this whole thing. And then Louis Baker, he came up coming from coroutine area. He came up with several proposals to combine the problems of signaling a stop in coroutines and cancellation and using callbacks with my proposal, so that in the C++20 standard we have both stop tokens and jthreads. And of course, a couple of other people helped. Here are a few of them, beside all the groups like the concurrency working group, the library working group, etc., who did a lot of tasks. That's it. So you can find the slides. I think I just answered the first question on that. The slides are already available for download. I only saw one bug in one slide, so it's okay probably to download them now. So josuttis.com, download CppOnSea. You will see the slides as a PDF file. And another advertisement, there are more details about move semantics in a workshop, a full-day workshop and the CPP conference next Monday, if you're interested in some of that areas. We only saw a few of them. That's it. Thank you very much. And I might have time, 1 minute, to come up with Q&A. Should I finish in time? So it's 12:30, Phil, or can I answer 2 or 3 questions now? And I have no idea how you tell me the answer of this question. You're there. So, so maybe I take the last question that was asked. Will there be a C++20 book? Yes, I'm working on it. In 3 years, we might have that. And the stop token is still cheap to copy because it's a shared pointer. It's as cheap to copy as a shared pointer, which is not that cheap. So you saw some move in the code, but copying a shared pointer is not the cheapest thing, but also not the most expensive thing. So you should avoid it, but it's not that expensive. If you're, yeah, that's it. Good.